In this example, we again are going to find the radius of convergence and the interval of convergence for the given power series. In this series, we have the sum from n equals 1 to infinity of the term -1 to the n power divided by n times 5 to the power n plus 1, all times x plus 2 to the n power. As usual, we are going to use the ratio test to solve this problem. So we are going to look at the fraction a sub n plus 1 divided by a sub n, and then take the absolute value. This gives us the absolute value of -1 to the power n plus 1 times x plus 2 to the power n plus 1, all divided by n plus 1 times 5 to the power n plus 1 gives us n plus 2. Then, rather than dividing by a sub n, we will multiply by the reciprocal of a sub n. So we'll multiply by n times 5 to the power n plus 1 divided by -1 to the power n times x plus 2 to the power n. Now we need to simplify. Because we are taking the absolute value of this expression, all of these factors of -1 will be eliminated by the absolute value, so we can just ignore those. Now I'm going to collect factors that are similar to one another between the top and the bottom of this fraction. Because I have x plus 2 to the n plus 1 on top and x plus 2 to the n on the bottom, this leaves me x plus 2 on top. The powers of 5 to the n plus 1 divided by 5 to the n plus 2 leaves me a factor of 5 in the denominator. And then we have n divided by n plus 1. Because each other factor involves only positive numbers, the only factor that needs the absolute value is the x plus 2. So we can rewrite our expression as the absolute value of x plus 2 divided by 5 times the fraction n divided by n plus 1. Since we're going to take a limit as n approaches infinity, we'll multiply that second fraction by 1 over n on the top and on the bottom. This gives us the absolute value of x plus 2 divided by 5 times 1 divided by 1 plus 1 over n. As n approaches infinity, the fraction 1 over n approaches 0. And so our limit altogether, as n approaches infinity, is the absolute value of x plus 2 divided by 5 times 1 divided by 1 plus 0, which of course is just the absolute value of x plus 2 divided by 5. Now the ratio test tells us that our series converges if that limit we just got is less than 1. And our series diverges if that absolute value is greater than 1. Now if the absolute value of x plus 2 divided by 5 is less than 1, that means that the absolute value of x plus 2 is less than 5. This means that the radius of convergence for our power series is 5. We can also rewrite this inequality as -5 is less than x plus 2 is less than 5. And subtracting 2, we see that -7 is less than x is less than 3. So we know that our interval of convergence is the interval from -7 to +3. However, we don't know whether we should include the -7 and 3 or not. In other words, whether we should have a round parenthesis or a square bracket on each end. So we need to test those two cases separately. If x equals -7, then we're looking at the series of negative 1 to the n divided by n times 5 to the n plus 1 times the quantity negative 7 plus 2 to the n power. Notice I'm plugging in negative 7 for x. So we have the series of negative 1 to the n divided by n times 5 to the n plus 1 times negative 5 to the n. I can split up negative 5 as negative 1 times 5. So we have the sum of negative 1 to the n divided by n times 5 to the n plus 1 times negative 1 to the n, 5 to the n. Now when I multiply negative 1 to the n by negative 1 to the n, we would get negative 1 to the 2n. Because 2n is always even, we will always get positive 1. So we can ignore each factor of negative 1. And then we can cancel 5 to the n divided by 5 to the n plus 1 and get 1 over 5. Also, there is an n in the denominator. We can then pull out 1/5. We have 1/5 times the series of 1 over n, and we can recognize this as 1/5 times the harmonic series. Because we have a constant multiple of the harmonic series, we know that this diverges. Since our series diverges when x is equal to negative 7, we do not include negative 7 in our interval of convergence. Now we need to see what happens when x is equal to 3. If x equals 3, we have the sum of negative 1 to the n divided by n times 5 to the n plus 1 times the quantity 3 plus 2 to the n, or the sum of negative 1 to the n divided by n times 5 to the n plus 1 times 5 to the n. We can cancel n factors of 5, so we have the sum of negative 1 to the n divided by 5n. Again, pulling out the 1/5, we have 1/5 times the sum of negative 1 to the n divided by n, which we recognize as the alternating harmonic series. We know that this converges. The way that we show this is using the alternating series test. Because our series converges when x equals 3, we do include the number 3 in our interval of convergence. And so our interval of convergence is the interval from negative 7 to 3, not including negative 7 and including 3.